Okay, so we're gonna come back chapter 3. We're gonna talk about nomenclature, how to name everything. Make sure everybody hopefully knows how to do that. Let us get going. That is obviously a periodic table. That's a periodic table. And I think we talked about previously, but obviously very important here in terms of nomenclature, especially when we're dealing with sort of ionic bonding and covalent bonding. There are certain things, again, on the periodic table that have fixed positive charges and negative charges. So everybody in group 1 is a +1 charge. Group 2 is a +2 charge. Essentially, aluminum, for the most part here in group 3, is a +3 charge. Remember that as we kind of file our staircase in this area, coming above the staircase in the non-metal region, starting at group 5, those non-metals will be -3. Group 6, they're -2, and group 7, they will make -1. And again, we are talking above the staircase, non-metals, because as you can see here as well, below the staircase, we do have some metals hanging out and stuff like that. So again, it's those non-metals that will do that. Now, in terms of our transition metal region, and actually where I just kind of circled, those are again metals, and they typically have a variable sort of positive charge. But there is a 3-pack of sort of transition metals that do have a fixed positive charge, and it's right here, sort of backwards L. Zinc and cadmium, both of these guys will be +2. And if you hang a left over there to silver, it will be a +1 charge. So those 3 transition metals will have fixed positive charges. Pretty much all the other transition metals, as we'll talk about, obviously will have a variable type of positive charge. So this is really important in terms of the charges when we're dealing with ionic compounds and naming ionic compounds for those types of charges. Now, when we talk about the type of nomenclature we are going to talk about ionic compounds. And again, an ionic compound is a metal and a non-metal. And once again, as we talked about when we did bonding, we're going to get a transfer of electrons, creating a cation, which is positively charged, and an anion, which is negatively charged. And remember that when you do write the formula for anything that is ionic, anything that has a charge, the overall formula does need to equal 0 when you put the positive and negative together. So again, a reminder, like, calcium and fluoride, like we talked about, when we put this together, we do need to make sure that we have 2 of those guys to balance out the charge. And we do write our formula like this: +2 balanced out by the -2 that are supplied here. We do write formulas, right, with subscripts. Subscripts go to the element to the left. And again, if there is no subscript written, it is assumed to be 1. And then obviously everybody goes to the left there. So as we talked about, really the main thing of that is the reason we need to do that is for everybody, right, to achieve that noble gas configuration that we talked about in bonding. It allows everybody to get to the same electron configuration as those noble gases. The other type of naming we'll talk about really is covalent compounds, are molecular compounds, and that is typically between 2 nonmetals. And obviously, as we talked about in bonding, that's going to be our sharing of electrons is going to happen. So naming is also really important, that you do sort of identify what type of compound you're dealing with so that you could apply sort of the correct rules to naming when you get there. All right, so let's just talk about basic ions by themselves. If you have a basic ion by itself, which is obviously a cation if it's positively charged, we typically will just use the entire name of the element pretty much. So Na plus would be the sodium ion. Lithium with the +1 charge would be the lithium ion. And this would be the calcium ion. Now, if you are asked to write the formula for an cation, it should have the charges Otherwise, it's not an ion. So if you're asked to give the cation formula, you do need to make sure you include the charge in it. Anions are the same sort of deal. Anions, though, we use the root of the nonmetal name. We drop the last part and we replace it with IDE at the end of it. So Cl minus becomes chloride ion instead of chlorine. Br minus instead of bromine becomes the bromide ion. Sometimes we take a little bit more of the name out. Oxygen oxide ion. So anything that is negative will get the IDE treatment, especially if it's negative from the periodic table, going to be IDE. And as we talked about on the first page there, whenever we put anything together that has charges, we need to balance it out to 0 in the simplest way possible. In this case, we have +1 and -2, which means we need one more lithium there to balance out the charge. And that would give us, again, our proper formula here when we put them together. Again, +2 on this side balances out the -2 basically on that side. Any questions on that there? So here's a table, again, that shows all that. One of the unusual elements, obviously, is hydrogen. It actually could go both ways. So if hydrogen is positive, which it probably isn't most of the time that you see it, it would be the hydrogen ion. But hydrogen can be negative if it actually comes after a metal. So if there's like a metal and then hydrogen, it's actually the negative version of hydrogen, and that would be the hydride ion, IDE. All right, so let's talk about type 1 compounds here. And type 1 compounds are ionic, and it does involve a metal and a non-metal. So as we talked about here, we're going to get that transfer of electrons from a metal to a non-metal. And again, that's going to create our cation, which is positive, and our anion, which is negative. Pretty much whenever you have a metal involved in naming, it is always the most important thing. So the metal is always the most important thing to look at. It basically determines how you name things when it's involved. And a type 1 metal is one that basically has a fixed positive charge. So this is going to be a metal that comes from group 1, 2, 3, zinc, cadmium, or silver. So if you see your metals basically one of those guys, the good news is that's pretty much all you need to know in terms of naming. You will basically proceed to use the whole name of the metal, and then the non-metal gets the IDE treatment basically at the end of it. So if we look at CaBr2, when we look at this, calcium is a metal, Br is a non-metal, so that automatically tells me it's ionic. I want to look at the metal, which comes from group 2, means it has a fixed charge. That tells me it's type 1. And at that point, I could just proceed to the name. And this is calcium, which is the whole name of the metal. And again, our bromine becomes bromide. This is made up of a cation that is Ca2 plus, and an anion, by the way, that is Br minus, not Br2 minus, by the way. So it's just Br minus is the anion. The 2 means that you have 2 of those. It doesn't mean that you have Br2 minus, yeah? So again, if you have to write the formulas for the anions, you want to make sure that you do it right. The 2 also, as you can see here, has absolutely, positively no effect on the name. So do not put di. Don't put a prefix. Yeah. People like to go calcium dibromide because di sounds cool. It's not cool. It's going to get you an X. So don't do it. Yeah. So do not use a prefix. If you are using a prefix in this type of situation, just put an X on it yourself because it's going to be wrong. So you could have 100 of the second guy, you could have 100 of the first things. There is no prefixes involved here in this type of naming. Okay. Has no effect on the actual naming part of it. Also why when we have something like NaCl, again, Na being sodium, which is a metal, Cl being chlorine, which is a nonmetal. Again, the sodium is the most important thing, which is a type 1, group 1, and that means that is, again, why we call this sodium chloride. Any questions on that there? So there's... All right, so why don't you try some? Why don't you give the names for each of these guys? Why don't you also write the formulas for the following? Let's do magnesium. We'll do magnesium oxide, lithium, sulfide, and I don't know. Let's do aluminum. Fluoride. And zinc phosphide. All right, so let's do names on the left and formulas on the right. Okay, so let's take a look, see how you're doing. We'll start here on the left. So again, really the first thing you want to do is sort of identify what you're dealing with. So K is potassium, that's a metal. Cl is a non-metal, which is chlorine. So right off the bat, you know it's ionic. You then want to focus in always on the metal, which is group 1. So that tells you it's a type 1. It has a fixed positive charge. So really you can roll right into the name at that point. We're going to use the whole name there of the metal, which is potassium. The chlorine will get the IDE treatment, and we'll have a little potassium chloride. That is made up of a cation that is K plus and an anion that is Cl minus in this case. Yeah. Any questions on that one there? Coming next, again, zinc is a metal. Sulfur is a non-metal, so it tells you it's ionic. Looking at zinc, it is a transition metal, but it's one of those threes that have a fixed positive charge, so it is going to be a type 1. So we could roll right into the name, which would be zinc, and sulfur will become sulfide, IDE at the end of it. Again, this is made up of a cation that is zinc with a +2 charge, and a sulfide with a -2 charge would be the anion in this particular case. Coming to our next one, we have calcium metal, Br non-metal, going to be ionic. Calcium is group 2, which means has a fixed charge, going to be type 1. So rolling right into our name, calcium and bromide. Once again, the 2 does not have any effect on the name, so no prefix here or anything like that. This is made up of a calcium cation with a +2 charge. Once again, the anion here being our Br minus, the 2 meaning that we need 2 of those Br minuses to balance out the charge. Lastly, here we have barium, which is a metal, hydrogen, which is a non-metal. And in this case, that means that this is going to be barium. And this is actually going to be the negative version here of hydrogen. So that's going to be hydride in this case. The cation here going to be barium with a +2 charge. The anion is going to be hydrogen with a -1 charge. And again, the 2 means we need 2 of them to balance out the charge. Any questions on any of those names? You'll be expected to know some of the polyatomic ions that we talk about. Yeah. All right. Coming to this side, we have the name, and we want to put it together. So we see magnesium and we see oxide. So that's a metal and non-metal, which tells you it's ionic, which means you basically have a cation and an anion. So you really want just the basic units of these things. So magnesium is group 2, means it's got a +2 charge. Oxide is oxygen, which is group 6, has a -2 charge. And once again, here we want to put together the equals 0. So in this case, we just need one of each to do that, and we'll end up with MgO. Lithium and sulfide, so metal, non-metal, ionic. So we need our cation, which is lithium. Group 1 has a +1 charge. And sulfide is group 6, which means it has a -2 charge. Once again, we do need to put it together to equal 0, and that means we actually need more of the positive guy. We need one more, and frankly, you can just count how many you have there, so that's 2. And 1s, basically, yeah. So it should look something like that, yeah. Aluminum, which is a metal, chloride, which is a non-metal, so we're going to look for our cation, that's group 3. And chloride is -1 from group 7. Once again, we do want to put this together to equal 0. And in this case, we need not 1, not 2, but we actually need 3 of those guys basically to put it together to balance out the +3 we got going on with the aluminum. So a little AlCl3. And lastly here, zinc, which is a metal, phosphide, which is a non-metal. Zinc is +2. Has a fixed charge. Group 5 for phosphorus is a -3. So when we put this together, that basically is a total of 6 we need. You get that by just multiplying the two numbers together. 3 times 2 is 6. So to get zinc to 6, we need not 1, not 2, but we need 3 of them. And to get the phosphide to 6, we need 2 of them, which will give us our formula of zinc 3, P2 in this case, yeah. Any question on any of those names? So sometimes people are taught the crossover move, if you will, like bring the charge down, bring the subscript up to figure out the charges. And I'll be honest with you, it doesn't really work 100% of the time. If you're good at like 93% of the time, you can just do that blindly and you'll get it right most of the time. But there's a lot of cases you will get it wrong if you just blindly sort of move things up and down. And again, what I'm talking about is people go like, hey, just move that down and that over there. And you'll end up with perhaps the right formula. Again, only really works about 93.4% of the time. There's a lot of cases where if you just blindly do that, you will get the wrong one. So personally, I think it's better just to think about it very simply. Just balance out the charges, and if it helps you to write out each of the ions and count up how many you have, that's a really good way not to get the wrong answer. Any questions on type 1 compounds here? Then let's go to type 2 compounds, which are also ionic, also metal and non-metal, also having that electron transferring. And again, we're going to get our cation and anion happening as a result of that. Once again here, it is the metal when it's involved that is the most important. And the metal in this case is most likely going to be a transition metal or just to the right under the staircase. And what these guys have in common is they have a variable positive charge. So, for example, something like copper in certain cases could be copper 1 and could also be copper 2. Something like iron could be iron 2 or iron 3. So, what we do, and also when I talk about just to the right of the staircase, that's kind of like where you have things like tin and lead and antimony, bismuth, in that area of the periodic table. Although they're not transition metals, they're below the staircase and they can have a variable type of charge as well. So when we have these things, there is slightly different than what we do with our type 1. We still use the whole name of the metal. We will still use the non-metal name that ends with the IDE. The difference is in the middle, we do use a Roman numeral. And the Roman numeral indicates the positive charge on the metal. So what it indicates is a very common mistake that people make is they think it indicates how many of those metals you have. And it doesn't. It indicates if you took one of those metals out, what the positive charge is on that particular metal. So if we had something like FeCl2, once again, I have a metal and a non-metal, which tells me it's ionic. When I look at the metal, it's a transition metal, which tells me it is type 2. The good news with this type of naming is you will always know the charge of whatever it is attached to. So you could kind of work your way backwards. So for example, here, I know I have an iron, but I'm not quite sure perhaps what the charge is. But I do know that Cl is group 7, and it should have a -1 charge, and there are 2 of them. So that gives me a grand total of -2. Remember, it doesn't need to equal 0, so obviously here +2 would be the charge that the iron has going on. We use the whole name of the metal, which is iron. We use a Roman numeral 2, not for how many we have, but again for the charge that's on the metal. And once again, no effect, the extra number down there, it is just going to be chloride. Once again, no prefix here either. So you should not use a prefix. Pretty much if you have a metal involved, you should not use a prefix, pretty much is the deal. And this would be iron 2 chloride. So why do we need to do that? We need to do that because if we have something like this, which is FeCl3, we have iron. We have now not 1, not 2, but now we have 3 chlorides. That's a grand total of -3. So in this case, the iron is actually going to be carrying a +3 charge, and that would be iron Roman numeral 3, once again for the charge, and once again, just going to be chloride. So because these metals can have a variable type of charge, you need to tell people in naming like, hey, in this case, we're talking about the guy with the +2, or in this case, we're talking about the one with the +3. Everything else is pretty much identical to what you would do in a type 1 situation. Whole name of the metal, non-metal gets the IDE. You just need to include the Roman numeral. The 3 exceptions to zinc, cadmium, and silver are considered type 1, so they do not need a Roman numeral because they still have a fixed charge, even though they're transition metals. That's why they fall under sort of type 1. Any questions on that there? All right, and here's again a few. Some of the weird ones sometimes that you come across, probably the most one is mercury. This right here, and this right here. Oddly, the one with all the 2s is actually mercury 1. The one with only 1 2 is actually mercury Roman numeral 2. The reason for that is mercury 1 is a dimer. It comes together, 2 mercury 1s together, which is why there is the extra 2 on the bottom, because there's actually 2 of them together, and each one is +1, which gives it an overall +2 charge. So how do you know if you're dealing with one versus the other? Typically, that 2 hangs around. Yeah, so the first one here is mercury 1. The second one is mercury 2. Does not have that 2 on the bottom. So typically that 2 on the bottom will stay there. And that's sort of how you kind of know that you're dealing with mercury 1 versus mercury 2 in this particular case. All right. That slide is clearly screwed up very badly, but I'll just there is sort of an old school way that we sometimes will name type 2 metals. So for example, if I had like copper 1 or copper 2, um, this would be cuprous, and this would be cupric. It's like if you had iron 2 or iron 3, that would be ferrous and ferric. Kind of the old school way of naming things, and they end in either OUS or IC. The IC, as you can see there, ends for the one that has the larger positive charge. So in the case of copper, copper 1, copper 2, copper 2 would get the IC. In the case of iron 2 and iron 3 would get the IC, along with kind of the older school type of way of naming. We will not use those. I would say cupric, cuprous, ferric, and ferrous are probably the common ones that sometimes pop up still. People very commonly use it. We will strictly use Roman numerals for it, so you don't have to worry about the kind of those older school names of it. But again, sometimes they do sort of pop into things and writings and stuff like that. So strictly Roman numerals, but that is sort of what's going on there. So why don't you try these here for each of these? Why don't you give the name And then why don't you also give the formula for the following? Let's do iron 3 oxide. Let's do actually let's do 10 for sulfide. Also do PbO2 over there. And let's do like nickel 2 chloride. All right, so guys, on the left there are some names, and on the right there, look, we'll start here. So again, identifying what you're dealing with. Cobalt's a metal, chlorine's a non-metal. So once again, that should tell you it's ionic. Cobalt is the metal, so that's what we want to look at, is smack dab in the middle there of the transition metal region, which will tell you it is type 2. So that tells you don't really know the charge. You need to figure it out. So we do have just one cobalt. We do know that it's attached to chlorine or chloride, which is group 7, and there are 3 of them, which gives you a -3 overall. That means to balance it out to 0, our cobalt does need to carry a +3 charge in this case. And that means we can then roll into the whole name of the metal, which is cobalt. We're going to do a Roman numeral 3 once again for the charge on it. And again, the chloride at the end with no prefix. And that would be cobalt, Roman numeral 3, chloride. Any question on that name there? Coming over here, that's copper, metal, iodine, a non-metal. Once again, that's ionic. And type 2, because the copper also sort of in the transition metal region there. So in this case, copper, we just have one. And we just have one of I, which is group 7, which means it should have a -1 charge. That means very simply to balance it out, the copper needs to have a +1 charge. That means we could then roll with our name, which is copper. Here we're going to go with Roman numeral 1 because of the charge. And we will put the IDE at the end of iodine and drop a little bit of it. And we get copper 1 iodide. Any question on that one there? Next one is tin, which is SN. That is a metal, and a non-metal, which is bromine. If you look at the periodic table, tin is just to the right of the transition metal, but it is underneath that staircase. And again, although they're not transition metals, they basically kind of behave like them in the sense of variable charges. So here again, we'll just make it not too complicated. We got 1 tin. We have Br, which is group 7, -1. And frankly, there are 4 of them, which is going to give us a -4 charge. That means in this case, our tin is carrying a +4 charge, and this would be tin Roman numeral 4. And once again, no prefix, so bromide in that case. Lastly, here we have PbO. Pb is lead, which is again just to the right of the transition metals, and oxygen is a non-metal, so that's a ionic compound, type 2. Here, same idea. We have 1 lead, and oxygen is actually group 6, which means it has a -2 charge. And by the way, that is -4, and that means that our lead is carrying a +4, not a +2, like a lot of you probably have in your paper for just blindly switching the charges. So this is an example. If you just blindly kind of move this up and that up, you're going to get the wrong answer in this case. So make sure you do understand what you're doing. This would be lead Roman numeral 4, and this would then be oxide. So again, kind of the just moving it up and down doesn't work 100% of the time. Yeah. Any questions on any of those names here? Yeah. All right, rolling to the formulas here. We could just use the name. We see Roman numerals, so we know it's type 2. But also the benefit of the Roman numeral is we already know the charge on this guy is going to be a +3 because of it. Oxide is oxygen, which is group 6, is a -2. Once again, here we need to get to 6 by multiplying the 2 numbers together. 3 times 2 is 6. Get our oxygen to 6, we need 3 of them. And get our iron to 6, we need 2. And then we just count up what we got. We got 2 irons and 3 oxygens. And we will have our correct formula happening there. Coming to the next one, that is tin Roman numeral 4. So that is SN with a +4. That is what the charge means. Sulfide is group 6, which is a -2. In this case, we do need to get it to 4. And that means we actually need more of the sulfide to do that. And that would give us an SnS2 in this particular case. Yeah. Lastly, here we have nickel 2. So that's a nickel with a +2 charge. Chloride is -1. And again, we want to get to 0. So we will need one more of those guys. We have 1 nickel and 2 chlorides in this case. Any question on any of those formulas, how we get it? All right, so just keep it simple. Yeah, if it helps you to write it out, all the ions like I do it. Don't make it more complicated than it should be. All right, any question on type 1 or type 2 compounds here? So here's a little decision tree. Basically, it's always, again, that metal that's most important when you have a metal involved. And if that metal is a fixed charge, you basically could just roll into the name and non-metal. If it is a type 2, you do, again, need those Roman numerals because it has a variable charge. That brings us to polyatomic ions. Polyatomic ions are actually groups of non-metals together that have charges. So if we look at NH4 NO3. This is actually 2 polyatomic ions that are here. And if we break it up right about there, this guy is NH4 plus, and this guy is NO3 minus. That one nitrogen, hydrogen, 4 hydrogens will all stay together, and it has a +1 overall charge. That one nitrogen and 3 oxygens will all stay together and has a -1 charge. We actually drew both of these, I think, in the last chapter when we did Lewis structures. That is this guy. They are actually sharing electrons, but still have an overall charge. And that is this guy. Those are really 2 ions. So this is an ionic compound happening. So it's kind of a weird mixture of something that is covalently bonding, sharing electrons, but overall has a charge. But when you put 2 of those together, you will end up with an ionic compound. So there is no sharing of electrons between these 2 things. It is those charges that hold them together. But within each of the polyatomic ions, there actually is sharing of electrons and covalent bonding happening. Based on formal charge and other things, like things can end up, obviously, with an overall charge. The good names of this is these guys do have names. So NH4 plus is the ammonium ion. Not to be confused with ammonia, which is NH3. This guy here is the nitrate ion. And really the good news is when we put these together, we're essentially taking +1 and -1, which is why when we look at the formula, we only need 1 of each. And when we have a polyatomic ion, no matter how many of the polyatomic ions we have, we just use the whole name of them. So this is going to be ammonium nitrate. So ammonium nitrate would be the name of this guy. We use always the whole name of the polyatomic ion. Again, like I said, regardless of how many there are of it, we don't put any prefixes or anything on this. The truthful idea here is, for the most part, NH4 plus is one of the few positive polyatomic ions that you'll come across. There are a few others, but NH4 plus is pretty much the only kind of positive one. In a lot of cases that you'll come across, there are a few others, which means in probably 9 times out of 10, or even more than that, you will be dealing with a combination of a metal and a polyatomic ion coming together. And that is most likely what's going to happen. The metal going to be the positive cation. The polyatomic ion in most cases is going to be the negative anion, which means, as we've been talking about, whenever a metal's involved, it is the most important thing, and also most important when you're dealing with polyatomic ions. So we fall back to our type 1 and type 2 rules when we have a metal and a polyatomic ion together. So if the metal's a type 1, you don't need a Roman numeral, and you just use the whole name of the metal and the whole name of the polyatomic ion. If the metal is a type 2, you will need to figure out the Roman numeral, use the whole name of the metal and the Roman numeral and the whole name of the polyatomic ion. So pretty much I would say most of the time that's probably how you'll deal with polyatomic ions, is it will be basically attached to a metal. So we do sort of fall back on those rules. So here's a table, and there's a couple up on Canvas and the exam 2 that has most of these things. But there are some polyatomic ions here that you do have to know the names and the charges that go with them. The best way is memorization, and also you can kind of group things together, and that makes it a lot easier to try to figure out maybe what the name is. So for example, if we look at NO2 minus, NO3 minus, this is 1 nitrogen, 3 oxygen with a -1 charge, 1 nitrogen, and 2 oxygen with a -1 charge. Top guy is nitrite, bottom guy is nitrate. We look at SO4 2 minus and SO3 2 minus. Sulfur and 4 oxygens all together with a -2 charge. That is sulfate. Sulfur and the 3 oxygens together is sulfite. When you're looking at a grouping of kind of 2 that are related to each other, the one with the most oxygen will typically end in 8. And the one with the least oxygen in a group of 2 will end in ite. As we see here, 2 oxygens, ite, 3 oxygens, 8, 4 oxygens, 8, 3 oxygens, ite. So that's a really good way to remember these guys. Sometimes people will, frankly, just remember, for example, all the 8s. And know if you need an ite, you just take off an oxygen. Everything else stays the same. Charge stays the same. Everything stays the same. You could just take off an oxygen from it. Or if you want to remember all the ites and you need an 8, you just put on an oxygen. Everything else stays the same. The charge stays the same. So that's a good way to sort of remember it without remembering every single one. You could just know how to sort of adjust the one that you did remember, either up or down, depending on sort of which way you're going. There's also groupings of 3 or 4 that are related to each other. For example, ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. So in this group of 4 that are related to each other, they all have a -1 charge. All those guys stay together as whole units. They move around as whole units. They never break apart into individual elements, because they are polyatomic ions and covalently bonded together. We break this right about here. Everybody to the right has the least number of oxygens, which means they should end in ite. So this would be chlorite. This guy would be chlorite. You obviously cannot have the same name for 2 different things. So when you have a grouping of 4 together that are related, the one with the least number of oxygens ends in ite, but also starts with hypo. So that is hypochlorite. Same thing if we go to the left, these 2 have the most oxygens, which means they should end in 8. So this would be chlorate. This would then also be chlorate. And once again, we can't obviously have the same name for 2 different things. In a grouping of 4, the one with the most oxygens will also start with per. So that is perchlorate, chlorate, chlorite, and hypochlorite. The only difference between all 4 of those things are pretty much the number of oxygens, right? So again, you could do the same sort of idea. You could go, remember chlorate, for example, is ClO3 minus, and know, okay, if I need chlorite, I take off an oxygen, is ClO2 minus. And if I need like hypochlorite, that's way down the road, one more, I take off another oxygen, I'm down to ClO minus. Or if I have chlorite and I need per, that means more, I add an oxygen to it. Chlorine is the non-metal in all these. You could substitute out chlorine for any halogen. For example, if I had BrO3 minus instead of chlorate, that would then be bromate. So it kind of works the same way. That would be bromate. By the way, if I add IO3 minus, I is iodine, and that's would then be iodate. So you could switch out the halogen in that grouping of four, basically named the same way, by following those things. Other things that happen here is, for example, if we had carbonate, CO3 2 minus, that is carbonate. And if you put a hydrogen on carbonate, you get HCO3 minus. That's an H and a +1. +1 and -2 is a -1 left over. We basically put hydrogen on there, so this is known as hydrogen carbonate. And of course, hydrogen years ago and still used is sometimes not used, and bi is used instead of hydrogen, and that is sometimes known as bicarbonate as well. There are some polyatomic ions that do end in IDE, like OH minus. That is hydroxide, IDE. CN minus, that is cyanide, IDE. A vast majority, though, of polyatomic ions will end in either ate or ite, but some do end in IDE as well. Any questions on that there? So let's see here. Let's do this. I'll clear this out maybe. Let's try some here. Let's go with what is the name for the following? Let's do a little NaNO3, a little CaSO4, a little FeOH3. And why don't you also give the formula for copper 2 chlorate. Let's do magnesium hydrogen sulfate or bisulfate. Let's do iron 2 hypobromite. All right, so write the formulas for the bottom three and the names for the top three. Actually, let's do one more. Let's do let's do ammonium sulfide. Yeah. OH minus is hydroxide, yeah. Okay, so let's take a look. We'll start here at the top. We got Na, which is a metal, and we have NO3, which is a polyatomic ion. So once again, as we talked about, the metal is the most important thing. So that is a type 1 metal, which means it has a fixed charge. And that polyatomic ion is NO3 minus, which is why we really only need one of each of those, +1 and -1, to get to our formula. Because the metal is type 1, we just use the whole name of the metal, which would be sodium. And once again, we pretty much just use the whole name of the polyatomic ion, and that would be nitrate in this case. Any questions on that name there? Coming to the next one, Ca is calcium, which is a metal. SO4 is sulfate, which is a polyatomic ion. It'll be broken up right about there. Once again, that metal, which is group 2, is a type 1. It has a fixed charge, which means we could roll right into the name, which is calcium and sulfate. And again, we have one of each because calcium is +2 and sulfate is -2. So +2 and -2, we just need one of each for the formula. Coming down to here, that is iron, which is a metal. OH is hydroxide, which is a polyatomic ion. In this particular case, though, our metal is a type 2 metal, which means it does have a variable charge. So we do need to figure that out. We got an iron. We do know that hydroxide is OH minus, and there are 3 of them. And that means that we end up with a -3. That means to balance it out, our iron has to be +3 in this case. And then we would roll with iron. We would need the Roman numeral 3 for the charge. And we would go with hydroxide here, the whole name of the polyatomic ion. We also see that when we look at the formula, because we have multiple polyatomic ions, we do not write the formula like this because that would imply that we have just 3 hydrogens, right? And 1 oxygen. So whenever you have more than one polyatomic ion, you do need to put parentheses around it in the formula and a little subscript on the bottom. And that implies that we have 3 of the OH minus units rather than just 3 of the hydrogens. So if you have more than one polyatomic ion, you need to put parentheses around it, number on the bottom. If you have just one, you don't need to do that. Any question on any of those names there? All right, rolling here, copper Roman numeral 2 means we do have a copper with a +2 charge. Chlorate is ClO3 minus. So we are essentially putting a +2 and a -1 together. We do need one more of those chlorates to get us to -2 and +2. That means that we should end up with Cu. I will need parentheses here and a 2 on the bottom. That tells me I have 2 of the ClO3 units and 1 of the copper 2. Question on that one there. Coming over here, magnesium hydrogen sulfate. Magnesium is group 2, which has a +2 charge. Now, if you're not sure, hydrogen sulfate or bisulfate, they're sometimes referred to as either one. And perhaps again, you know that sulfate is this guy. Hydrogen means you put an H plus on it, which means that should be hydrogen sulfate, that guy right there. And that also will have a -1 charge, which means I do need 2 of them to balance it out. And that will give me MgHSO4, and again, a 2 on the bottom there to make it correct. Any questions on that there? Iron 2 hypobromite. So iron with a Roman numeral 2 is what that means. Hypobromite, I know bromite is BrO2 minus. So hypo is the least. So BrO minus is probably what I'm looking at there for my hypobromite. Bromite, ITE. And that means that I do need 2 of them. So we will end up with Fe parentheses BrO and a 2 that is happening in that case. Maybe I'll go a little bit higher here. Fe BrO2. This case. All right. Lastly, ammonium sulfide. Ammonium is this guy right here, NH4 plus. Sulfide is from the periodic table. It is sulfur, group 6, -2. So putting those together, we actually need one more of the ammonium. That means we do have 2 of those. So we do need a parentheses and an S in that particular case. Yeah. Any questions on any of those? So for the most part, as you can see, most of the time I would expect a metal to be involved with your polyatomic ions. So you want to fall back on the type 1 or type 2 rules. This, by the way, is probably the only place where you could use a prefix and a metal together, and that is because the name of the polyatomic ion, like dichromate, has a prefix in it. That's the only time that that would happen, is only because the polyatomic ion's name actually has the prefix in it. Other than that, if you find yourself prefixing and with metals, you're probably doing it incorrectly. Any questions on polyatomic ions? Once again, you are responsible for the list here. And again, there's a bigger list, I think, in exam 2 module of just the polyatomic ions and stuff like that. Yeah. Anything that's on the chart is fair game. No? Okay. Other questions? Okay. All right. Then let's talk about acids and how we go about naming acids. Acids are any substance that produces H plus ions in solution. That is the hydrogen ion. It is also referred to in acid-base chemistry as a proton, and it is something that has the ability to basically produce free-floating H plus, which you'll learn all about when you take 200B acids and bases. But it is called a proton because hydrogen has one proton, one electron, and no neutrons. So in order to become positively charged, it has to lose an electron. So the only thing left is a proton, which is why it's sometimes referred to as a proton. How do we name acids? Well, frankly, it all involves whether or not oxygen is involved. And when we do write acids and formulas and stuff like that, because it really is always an aqueous environment, we do write aqueous next to the formulas, and you usually will see aqueous written. And that tells you that it's an acid. It's not like in the gas state or anything like that, for example. So let's talk about when we do not have oxygen. So if you look at an acid and there is no oxygen, that acid is going to start with hydro something ic acid. So that is the general formula for how you name acids with no oxygen. So for example, if I had HCl, and by the way, for all acids, the cation is H plus. So H plus is always the cation, the positive guy in an acid. Although in reality, in certain cases, we think about HCl as covalently bonded. In the aqueous form, when it goes for a swim, it will break apart and that H will come off. So we think of acids as being more ionic than necessarily sort of covalently bonded. So when we do this, there is no oxygen. So this is H plus, our anion is Cl minus. So this would be hydrochloric acid. The missing part will come from the anion in this case, which is chloride. So that would be hydrochloric acid. But HBr, that would be hydrobromic acid. Again, this being Br minus and H plus basically together. So no oxygen. We'll start with hydro. We'll end with ic acid. The negative anion is the missing part in this. So why is the aqueous important? And that's because if I had something that was just HCl, say in the gas phase, when we have hydrogen involved, we think of it like a type 1, which means we would call this hydrogen chloride gas. So that is hydrogen chloride gas, also H plus and Cl minus. But in the aqueous state, it becomes an acid and it is hydrochloric acid. Same thing, by the way, since we're talking about hydrogen, if you had hydrogen, 2 of them, for example, something like this. This would be hydrogen sulfide. Whoops. Hydrogen sulfide gas. deadly toxic gas, which they no longer use next door, so that's good. But this is hydrogen sulfide. The cation would be H plus, and there would be two of them to balance out the -2 charge. You can see with hydrogen, if it's not an acid, or even if it is in a non-acid form, even if there's multiple hydrogens, we still just do like a type 1 thing. We just use hydrogen. It doesn't matter how many there are. By the way, if I had H2S in the aqueous form, this would be what acid? This would be hydrosulfuric acid. Yeah. So in the acid form, very different than sort of in the gas form. And again, in the gas form, hydrogen, just hydrogen, or whatever the negative guy is. All right, so no oxygen, hydroic acid. Now, if the acid does have oxygen, if it is yes to oxygen, it most likely will contain everybody's favorite thing that we just talked about, a polyatomic ion. These are sometimes referred to as oxyacids because they contain oxygen. And as we talked about, for the most part, your polyatomic ions will end in one of two ways, either ate or ite. And if your polyatomic ion ends in ate, your acid name will be something ic acid. So for example, HNO3. NO3 is NO3 minus, which is nitrate. This becomes nitric acid in this case. Yeah. If you had H2SO4, SO4 is SO4 2 minus, which is sulfate. This becomes sulfuric acid. The reason we have two hydrogens is we need it to balance out the charge, right? +2 to balance out -2 in terms of the charge. So when you put the formula for a acid together, you just think of it like a ionic compound with H plus always being the positive guy. There is no hydro here, yes? So oxygen, no hydro happening on these names. Now, if you had your polyatomic ion and it ended in ITE, it is something OUS acid. So if you had HNO2, NO2 is NO2 minus, which is nitrite. This then becomes nitrous acid. If you had like H2SO3, SO3 is SO3 2 minus. That is sulfite. This will become sulfurous acid in this particular case. Again, same deal as on the other side, H plus, two of them for this guy, and one H plus for the cation for that particular guy. Bless you. So again, if you have oxygen and it is an acid, no hydro. So either ic at the end or us. You could feel like you ate too much and you feel icky. It's a good way to remember that, right? So ate ick, ate too much, I feel icky. And again, if you do have no oxygen, then that is where the hydro is. Again, we don't mix any of those two. Any questions on that there? So let's take a look at a couple. Let's look at what is the name of HI? How about HClO4? Let's do, what is the formula for phosphoric acid? Let's do hypochlorous acid. All right, so it's the name on the left and formulas on the right. So let's take a look. We'll start here. By the way, we know it's kind of an acid. We see the aqueous symbol, AQ, next to it. We know for sure that the cation in an acid is H plus. That means that I is group 7, which would be I minus. More importantly, though, we do not see oxygen here. So we know that this should start with hydro. The negative guy is going to determine the missing part. So hydro ionic. And this is going to be acid in this case, right? Question on that one there. Looking at the next one, again, we know it's an acid. So we got H plus. That is actually going to be ClO4 minus. That does have oxygen in it, and that is a polyatomic ion. That is perchlorate. ATE means that my acid should then become perchloric acid. We do still keep the front part there of the polyatomic ion on the name. No hydro because it has oxygen. Any questions on those two? Now, if you have the name of the acid and you need the formula, the easiest thing to do is just to remember how you get to those names. So I first off do not see any hydro here. So I do know that it contains oxygen, and that means it has a polyatomic ion. I also know that ick means that I ate too much, and I put an 8 there, and now I see that that's basically like phosphate, basically. And that tells me that my acid should be H plus and my polyatomic ion should be phosphate. So now all I have to do basically is put that together, and we will need 3 of these H pluses to balance out the -3 charge of phosphate, and we will end up with something just like that. So you can kind of work backwards and kind of put the name there, and you'll be able to kind of pretty much figure out the polyatomic ion you're dealing with. So if we take the same approach here, there is no hydro, which tells me it's oxygen involved and a polyatomic ion. OUS means ite. So that is hypochlorite, right? So that basically is going to be our ClO minus, and our H plus would be our acid part of it. And putting those together, we would just need 1 of each of them to balance it out. We'll give it there. So when you're working backwards, you could kind of scratch out the last part of the name, put 8 or ite in, and you'll be able to probably figure out the polyatomic ion relatively easy that way. Yes. Why does, yeah, yeah, yeah. There's so we use hydro if there's no oxygen involved in the acid. Yeah. Other questions? Okay. All right. Questions on acids here. All right. All right. So we're nearing the end of naming here. Lastly, here is sort of lastly, but type 3 type compounds. Type 3 is covalent or molecular. This is where we have 2 nonmetals, and as we know from bonding, that is going to involve sharing of electrons. So after all the waiting for naming and after all the warnings of do not use prefixes, this is your place for prefixes. This is prefixes all day. So this is the proper place to use prefixes when we talk about prefixes, like mono is 1, right? Di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona, why not, is 9, and deca is 10. So deca, there you go. So we do use prefixes here. These are pretty much, I would say, the easiest ones to do, but also the ones people screw up the most on because they want to do all kinds of weird things they shouldn't be doing. So don't do weird things, just name them correctly. So let's talk about how we deal about naming these. Frankly, because they're sharing electrons, there's no ions. So you don't have to worry about balancing charges, figuring out charges. You frankly just need to see how many of each element you have and pick the appropriate prefix. And that's pretty much it. You pretty much will roll with prefix and the whole name of the first element. You will then roll with a prefix and the second name. We'll get the nonmetal with the IDE at the end of it. So basically prefix whole name, prefix IDE at the end of it. There are a couple of rules though. One rule is we do not use mono on the first name. It is okay on the second name. And the other thing that very commonly will occur is as you take the prefix and the first letter of the element, you will sometimes end up with two vowels in a row. So you'll end up with like a O and an O or an A and an O. And typically we get rid of the prefix vowel at that case. For example, if we had CO, carbon is a nonmetal, oxygen is a nonmetal. So as soon as you see that, that's two nonmetals. That tells you it's type 3. You don't have to worry about anything but writing what's there. And in this particular case, we have only one carbon, which the prefix would be mono, but we do not use it on the first name, so we would just call it carbon. We also have one oxygen, which the prefix is still mono. And we do use that on the second name. And mono, and then the second guy gets IDE at the end, oxide. So if you wrote it directly like this would be carbon monoxide, which doesn't sound right to us because we typically will drop that O and we call this not carbon monoxide, but carbon monoxide, yeah, with one O. And again, that's a very common sort of backing up. So if you get an O and an O together, drop the first O. If you get an A and an O, drop the A. Two I's are okay, actually. So if you got two I's together, it's okay. But those are typically the things that we do. There is no balancing needed. Just roll with the prefixes like you should. So as we see there, that's what we talked about. Here's again a table of those prefixes. And once again, that OO or AO, we want to get rid of that prefix sort of letter there. Now, there we go. There's a couple of those things. I'll add it in there. I guess it's pre in there. An example, if we had 4 oxygens, we would have tetra oxide. We would drop the A off of it. So instead of tetra oxide, we drop that A and it would be tetroxide here. Same thing with our mono. Now, there are some things that are always called by common names. And even though they are sort of nonmetals and nonmetals, H2O is water. It is not a trick question when you see it on the exam or quiz. Put water and move on with your life. Do not put dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide, right? It's probably why they don't use that name, I suppose. So that is water. NH3, which has no charge and not to be confused with the polyatomic ion, that is ammonia. Yeah. And the simplest organic compound you could have is CH4, which is methane. These 3 things you should always go with the common name. So it shouldn't be like nitrogen trihydride or anything like that. So again, just roll with the common name on those 3, water, ammonia, and methane. Any questions on that there? All right. So why don't you try naming these guys? Why don't you also write the formulas for the following? We'll go with a dinitrogen pentoxide. We'll do a carbon tetrabromide. And we'll do a dioxygen, make something up. Tetra sulfide. All right, so names on the left. Okay, so let's take a look and see So once again, we want to identify what we're dealing with. So I is iodine, which is a nonmetal. O is oxygen, which is a nonmetal. So as soon as you see two nonmetals together, that's a type 3 all day. And that should also be really happy because frankly, they should be really quick. You always have to figure out is the appropriate prefix. We don't have to balance out charges. So frankly, we have two I's. So the prefix for two is di. We do use the whole name of the first element, and that would be iodine. Prefix for 7 is hepta. And the second guy would be oxide. Here is a situation where we would want to get rid of the A here and just make it heptoxide here without the A in that sense. Question on that one there. Here again, the two I's are okay. Mainly it's the A and the O combination or the O and the O combination. Once again, if we look at the second one, we got carbon nonmetal, oxygen nonmetal. So that is prefix time. We have only one carbon, which is mono, but we do not use it on the first name. So this would be carbon, the whole name of the element. Prefix for two is di. And again, oxygen becomes oxide. So we get to carbon dioxide in this particular case. Lastly, here on the left, we have phosphorus, which is a nonmetal, Cl, which is a nonmetal. So again, that tells you it's type 3. One phosphorus, which is mono, do not use on the first name. So phosphorus. We have 3 for our Cl, which means tri. And again, IDE at the end of it. So phosphorus trichloride. Any questions on any of those names? Now, looking to the right, we have names and we want formulas, which in my personal opinion, probably the easiest thing you'll ever do. But also, again, the thing people screw up on. So when I look at the name of dinitrogen pentoxide, I see prefixes. That tells me it's type 3. I should just write what it says. So di is 2, nitrogen is N, so that's an N2. Penta is 5, oxygen is O, that's an O5. I am done in like 5 seconds, maybe, yeah. So don't overthink it, yes, and especially in this case, all you have to do is basically identify it. Carbon, no prefix, but I do see a prefix here for tetra, and they are both nonmetals, which tells us it's type 3. No prefix on the first one tells me there's just one, so you're going to go with a carbon. And tetra is 4, so Br4. There it is. And lastly, prefix. And as we know, this is the only place pretty much prefixes can exist. So dioxygen means I have 2 oxygens, and tetrasulfide in this made up thing, probably a little 4 oxygens going on. Yes, sir. Yeah, most of those like boron, all those guys on the upper side of the staircase will fall more non-metal. Like boron and all those guys will fall more as a non-metal. And again, kind of on the lower end will be on more of a metal type of situation, stuff like that. Yeah. Other questions? Questions on type 3 should be pretty straightforward. Yeah. All right. Last thing we're going to talk about here in terms of naming, yeah, is something we talked about the other day in that experiment, which was hydrates. And remember that when we have a hydrate, we basically have a salt part, and we usually have this little dot that's written and a water part, right? So for example, like we did MgSO4.7H2O. We basically named the salt part just like normal. So if it's a metal type 1 or type 2 and it's a polyatomic ion, so that's type 1, and obviously a polyatomic ion, so that's going to be magnesium sulfate. We use our prefixes like we just talked about, and basically water is named as a hydrate. So that's going to be heptahydrate, right? And if we had something that was more of a type 2 type situation, that is iron, which is type 2. So iron, not sure, but sulfate is a -2. So that's going to be a +2. So this would be iron, Roman numeral 2, sulfate. And once again here, tetra hydrate for the water. So hydrates, as we saw in that experiment, are named a little bit differently. They have a little different formula. They have this little dot that has the water part of it. Remember that the entire formula for the hydrate is all that together with the 7 waters and stuff like that. Question on naming hydrates there. Question on naming anything now that you are naming professionals. Yes. All right. So you should be able to name everything that you ever need to do